Okay, uh, welcome back everyone. We'll start the session within few minutes. Let's other also join. Okay, let's start the session. Let me share my screen. I guess others will join on time. So it's week 13. This will be our last tutorial of the session. And I hope you all are doing your assignments very well. And it's towards the end of the course we are. Right. Okay. So we were on the collocated grid part where we discuss about the interpolations, momentum interpolation, and linear interpolation. So momentum interpolation was the reach of interpolation, where I was telling about momentum interpolation, or you can say that Rishaw interpolation. Okay, where I was saying about that your interpolation can be written for the phase as u west is equal to u west hat u p hat over 2 plus EW minus EP. Okay, so we have written for the west phase. So I was let's move to some comments of that. Someone is trying to join. So let's come to the comments part. So UE and UW are the functions of adjacent pressure values, and continuity equation does not support pressure checkerboarding. Also, uh, that's a good news, as you know that, because we need to avoid the checkerboarding part. Then UE, UP, and UW momentum equations are still functions of non-contiguous pressure values. So momentum equations still support checkerboarding, but momentum interpolation result in artificial terms, which helps us. Okay, which helps us in solving the approach. So staggered grid approach can also be shown to have this diffusion-like term, and avoiding the oscillation because of the checkerboarding by modifying the continuity equation has an extra term, the fourth derivative of velocity diffusion terms. Okay. Now let's do a simple algorithm on the collocated grid. Okay, let's do that. Yes, I'm not visible. Now visible. Okay. Simple grid on collocated grid. Simple algorithm on collocated. So uh, we can we understood the momentum interpolation and how do we simplify the do the simple algorithm on collocated. Okay, so if you remember, we had two issues. One was there was no equation of pressure, and there was this problem with the pressure velocity checkerboarding. So the pressure velocity checkerboarding is now avoided using the Ricci interpolation. Whereas no equation for pressure still has to go through the simple algorithm. So now we need to modify our simple algorithm, or rather we applied for a collocated storage. So let us consider a two-dimensional Cartesian grid. And again, let us say that mesh is uniform for simplicity. And we are using a collocated grid. That means we are storing both the velocity components, that is u, as well as the pressure, temperature, and all the scales that are stored in the cell center. So this time, everything is stored in the cell centroid, and we are creating an additional velocities on the faces, that is east face and west faces. But they are additional set of velocities. Everything is otherwise stored at the cell centroids. Then let us look at the momentum equation. So momentum equations are basically, you know that. Let me write for two-dimensional Cartesian grid. I hope I'm unmuted, right? Okay. So I was here. For the two-dimensional, as someone has pinged. Any doubts? Rohit, do you have any doubt? Okay. So two-dimensional Cartesian grid. which is uniform. So the variable like u, v, t, p, or property phi, and so on are stored at the cell centroids. That is p. Okay. And the momentum equations in both x and y directions, if you remember. Del dot rho u is equal to del dot mu del u minus I dot del p plus am I connected? Hello? Yeah, I'm connected. Okay. So writing these two momentum equations. Mu del v minus I del j del p plus sv. Okay, so these are the two momentum equations. All right. So now to modify our simple algorithm, we apply it to a collocated storage. So we have considered a two-dimensional Cartesian grid. The mesh is uniform for simplicity. And you're using a collocated grid. That means we are storing both the velocity components, that is u and v, at pressure and temperature, everything in the centroid P. So as everything is stored at the cell centroid P, we are creating an additional velocity, which we call as US east and U west, but they are additional to set of velocities. Otherwise, everything is cell centroid. Okay. These are the two momentum equations, and including the source terms as well. Okay. Now let us discretize the momentum equation at the cell centroid so that in such a way, discretize momentum equations at cell centroid for P cell. That is APU UP is equal to summation of A and B U and B at U plus del Y by 2 PW minus PE plus BP at U. Similarly for V also we can write AP UP A and B of V and B plus del X by 2 PS minus PN plus BP V. This was U. Okay. And we write dividing by AP and of suppose I divide by AP on both the sides, so that will be summation of A and B U and B plus BP of U divided by AP of U plus del Y by 2 PW minus PE by AP of U. Okay. So now that means you have described the momentum equation for both X and Y. And to write that, basically you have the pressure checkerboarding that can be supported by the momentum equation. But we will use the momentum interpolation when we discretize the continuity equation such that these pressure checkerboarding would not be supported by the continuity equation. Then what do we do? Let us divide this by the coefficient of UP, and these are the equations. Okay. So I can then I can call this whole entire quantity quantity as UP hat, okay, and this quantity as dp hat, this whole dp of u. So I can write the equation as UP is equal to UP hat plus dp of u pw Okay, hello. Okay, we are back. Yes. Yeah. All right. Connected. So I was saying that we can write this whole term as UP and this term as DP. Okay. So my equation come out to be like this. And similarly for the y direction as well, we can write. So similarly, VP is equal to VP of hat plus DP of V by 2 into PS minus PN. We got this two discretized momentum equations. All right. Now we have these two equations that are just written in a slightly different way. Let us perform momentum interpolation to obtain the phase velocities. That means we already know uh, we already know, that is UE and UP, and VP similarly. We can write the equation for UE. That will be UE would be UE hat plus DE hat times the corresponding values. Okay. So let me write momentum interpolation to obtain phase momentum equation for the phase velocity. So U east phase can be written as UE hat plus UP hat by 2 by the momentum interpolation we are doing. Okay, reach out. So DE into EP minus DE. Okay, and UE is equal to UE hat plus DE into EP minus PE, where you can write DE is nothing but DE, where your DE is E at U plus DE at DP at U by 2. Okay, and similarly U west can be written as like this. U west is equal to UW hat plus UP hat by 2 plus TW minus PP, okay, where UW is equal to UW hat plus PW minus PP, and where DW will be DWU plus DP of U by, okay. All right. Any doubts still here? You can ask. So we have removed the non-contiguous part and converted into the contiguous part by this kind of interpolation, where DE is proposed by the Ree and Chow as taken against the arithmetic average for the cell coefficients, right? That is dE plus dP by 2 or dW plus dP by 2. So what is DEU in this term? So this term will be del Y by AP for U cell, and DPU will be del Y by APU for the neighboring cells as well, which is average of all the Ds. Similarly, momentum interpolation can be done for each of the phase velocities, just like we had done for UE. We can do the same thing for UW. So UW would be UW plus UP by 2, and so on, the other terms we have done. Okay. All right. So similar, you can draw, it's a two-dimensional case. So for V north and V south also, you will write in the similar manner. I'll put it here. This and this. So V north will be V north hat plus T north Vp minus Pn, where Vn is Vn hat plus Vp hat by 2, and Dn is Vnv plus Vpv by 2. Similarly, your V south will be written like this. V south of V south hat plus Dn plus D south Ds minus Vp, and your Vs hat will be Vs hat plus Vp hat by 2, and ds will be dsv plus dpv by 2. Okay. So what we did basically, we wrote from the cell values. We wrote from the cell value and its neighboring values at the cell center. And we wrote this momentum interpolated phase velocities. These are not linearly or linear interpolation phase velocities. These are the momentum interpolation phase velocities. Because if this were the linear interpolated, then you would have the alternative pressure term, which is not there, as we have removed and being added. So these are now the momentum interpolated phase velocity. That means we have now the phase velocity on east, west, north, south, all that. Then what do we do if we use these phase velocity in the solution of continuity equation? So if we solve the discrete momentum equation, let us say U star and P star, then the converged U stars for the cell centroids for UP star, VP star field. Even if you construct for the phase velocity, which will not satisfy the continuity equation, that means the flow rate you would get is Fe star west, north, south, and the mass flow rate continuity equation will not be satisfied for any cell because these are basically coming from the solution of momentum equation for gas pressure values. So the idea basically is similar to essentially so simple only is basically you would wish to have these flow rates to be corrected or the velocities to be corrected such that it satisfies the continuity equation. And we want to address the corrections that is U star for east, west, north, south, U star and V stars for all the phases. Okay, so let me write. If we solve discrete momentum equations using U star, V star, V star, and converge UP star and VP star field, will not satisfy continuity equation. That means the flow rates for all the phases, Fe minus FW star plus Fn star minus Fs star is not equal to 0. So we would like to add some corrections such that the continuity for east, west, north, south is satisfied. Okay. It means we can split each of these into a star and prime notations. And because the star continuities would be known from coming solution of the momentum equation, then we would be able to send it the right hand. So Fp star minus of Fp star plus Fw star will come here. So let me write this equation in terms of stars and prime notation. So this can be written as Fe dash Fw dash Fn dash minus Fs dash minus Fe star plus Fw star minus Fn star plus Fs star. And these stars are the known. Then you know that Fe is nothing but rho u dash E delta y. So write for 1. So Fe dash will be rho u E del y. Similarly, your Fw dash and Fn dash will be rho Vn dash del x. And Fs dash will be, you can find out. Now, this is where the difference comes between a staggered mesh and a collocated mesh. So essentially now these prime velocities corrections, the velocity correction, we will get them from the momentum interpolated phase velocities. So we had just these interpolated velocities, that is UE and UE hat plus PE times some pressure difference, and a corresponding equation in terms of star. Let us say if you have guessed the velocity field and guess a pressure field, then there is a star missing. So if you have guessed velocity field and a guessed pressure field, I was saying, which you can write the guess velocity field as UE star is equal to UE star head plus D into PB minus PE. So basically, these two equations are basically the momentum interpolated phase values for the east phase. One is without star and one is with the star. And the guess velocities, that is we have. And another one, which is basically supposed to satisfy both momentum and continuity. The discrete momentum and continuity equation means if you subtract from one, that means UE minus UE star, you will get the prime value. Okay. Any doubts still here? Which is equal to UE hat minus UE star hat would give you UE dash hat as well, plus DE times the pressure differences. So let me write here. But from momentum interpolated phase velocities, we have UE is nothing but UE hat plus DE into PP minus PE. And UE star is nothing but UE star, similarly, DE PP star minus PE star. Okay. So subtracting these two, you will get the in terms of prime. So if you subtract these two, what you will get? QE dash is equal to QE R dash plus DE into PP dash minus PE dash. And this will be 0, that use the contribution from the neighboring terms. Contribution will be 0 as per the simple. Contribution A and B, U and B prime from simple. Okay. We have got the velocity corrections. So your velocity corrections are U prime and B prime. This U prime and B prime similarly. Velocity corrections. UE prime is E into PP prime minus PE prime, and UW prime is equal to EW into EW prime minus PP prime. And similarly, in terms of flow rate, you can write. Right. So if I write in the terms of flow rate, this will be FE prime will be rho del Y PE into PP prime minus PE prime, and FW is equal to rho dW into del Y into PW prime minus PP prime. Okay. So these are your velocity correction. Similarly, you can write for the north and south face as well. So V north will be D north PP prime minus Pn prime, and V south prime also you can write. And Fn prime will be rho dW del X PP prime minus Pn prime, and Fs dash you can also write. You can substitute each of these in the above equation. This equation we have formed. Suppose this is your equation 1. You substitute all these values above the prime notations in equation 1. Substitute in equation 1. Okay. So just substitute and tell me what it will come. What will be the answer? Just take a minute and tell me. So anyone has done? Simple. Okay. It is. I hope you might have solved it. So after substituting in equation 1, what will you get? So equation will come out to be in the form of AP EP dash is equal to summation of A and B dash plus B. And your AEs will be rho dE del Y. AW will be rho dW del Y. A north will be rho dN del X. A south will be rho ds del X. Your AP will be AE, AW, A north, A south. Your B term is in terms of star values of the flow rates, Fe star plus Fw star, Fn star minus F star. Okay, more than. All right. So that means we have now related them to the pressure corrections. And now what do we do? Basically substitute for all these flow rates back into the equation 1. That means on the left hand side, you have everything in terms of pressure correction. On the right hand side, you have in terms of star velocities. So we have all of this ready. The difference between the staggered mesh and the right, the one we have right now is basically is these DE that we are different and DNs are also different. The prime P primes DN come as arithmetic average of DE plus DP by 2 and so on. Right? So whereas the second grid we already avail because the U E is already stored at the E sphere, we are doing the same thing, but to interpolation not having grid as it is created, which will be helpful. when we go for the curvilinear meshes. And we don't have to solve on any faces, but we kind of solve on the cell centroid and so on. So essentially, we substitute for these Fe, which you basically get in terms of AP, PP prime, okay, this equation, where your coefficients are like this. So this is the pressure correction equation. Once you solve this, you would get all the pressure corrections. And the pressure corrections can be used to correct the velocity corrections to obtain the velocity corrections and the flow rate correction. And these corrections can be added to the star values to obtain the correct values for phase velocities and phase flow rate. So that is precisely the simple algorithm on collocated grid. And let us see what is the overall algorithm once again. So we put all the things together when we see how the final simple algorithm will look like on the collocated grid. So we start off with guessing the velocities and the pressure at cell centroid. So this is basically give the cell centroid values of velocities and pressure. That is UP star, VP star, PP star. And in addition to that, you will also guess the U and V at the east and north faces, as well as on the pressure values at the faces. Only on the velocity on the faces, because the only velocity you will store, not the pressure, in calculating stars, that stars. And there is also needed to be kind guess. Then you have to solve for the momentum equation at the cell centroid. That is basically your APUP star. Okay. We guess these values, solve for the momentum equations, APUP star summation of that and that equation. Then using the momentum interpolation, calculate the U stars from that momentum equation. From that U stars values, you calculated the flow rates value that will eventually be converted into a B term. Then you solve the pressure correction, correct the pressures, correct the flow rates. Okay, then correct the cell pressure using some under relaxation if you want. Then correct the cell velocities to improve the conversion, solve additional scalar transport equations, then check for the convergence, and if it is not converged, then go to step 2. Then you solve for the additional transport. Okay, step 2. All right, any doubts in this whole of the algorithm on the collocated grid? So we'll start with a example problem of a tank or simple algorithm on the collocated grid. So I'll write the problem and I'll give you some time to solve it and then we will discuss. So the problem is the 1D flows, the 1D flow through a porous medium. The equation for that is given like this: C mod U plus dP by dx is equal to 0, and d by dx of UA is equal to 0. Then you have the cell system is like this. So this is your P, in front this is your C. So this is 1 to 3. Your x direction. Okay. And it is given that del x for the grid is equal, that is x2 minus x1 is equal to x3 minus x2 is equal to 2. A1 is given to be 6, A2 is given to be 4, A3 is given to be 2. Then your U1 is 10. See the boundary velocity conditions. Boundary conditions. Okay. Need to calculate U3, sorry, UB, PB, QC, PC, and boundary pressures P1 and P3. Initial gas is given. UV star is equal to UC star is equal to 15. And PV star is equal to PC is equal to P1 is equal to P3 is equal to 120. Okay, so you have to discretize and solve this question. Zoom out. This is your question. Take a few minutes. Try to solve it. Else we will also solve. Okay, I guess let us solve. Let us now discuss the same. So essentially, we will first set up a problem that we need to solve it. This is your problem. We are we are reformulating the problem for the colligated grid with a one-dimensional flow through a porous medium governed by this equation, where C is nothing but your constant that represents the porosity of the medium, and continuity equation is given by the second equation. We have given both the equation, and then now we have, unlikely the staggered grid, we have the collocated grid. Here we have two cells, that is B and C here, where the velocities and the pressure are stored. So UB, PB, UC, PC are all stored at the cell centroid. Let me write here. UB, PB, and UC, PC as cell centroid. We have three phases 1, 2, 3, which are basically west, east for B cell, 2, 3 from the west, and these for the C cell. Now in it, on these phases, you would also need the velocities U1 and U2 and U3, which would be utilized in writing the continuity equation for cell C and cell B. We would also need to keep the track of these velocities, and we would need pressure on the faces, that is P1, P2, P3. Okay, I'll write it here. U1, P1, Q2, P2, Q3, P3. Okay. Now the other problems are given. The variables are given in the problem. Grid spacing is given to be 2, and the cross-sectional areas are given. The value of C at all the location C1 equal to C sub 1 minus 1 equals C sub 2 and so on. And all the C's can be taken to be constant. And it can also be even at some CB and so on. So this can be taken into constant. And the boundary conditions are given. That is, the velocity at the phase 1 is given as 10 units per second, and on 3 is given as U3 equals 30 meters per second. What we see is the both boundary condition that are given for the velocity. So essentially, there is no boundary condition for pressure that is given in the problem. And the question says that you calculate the cell velocities and the cell pressure, that is UB, PB, UC, PC, as well as we are asked to calculate what is boundary pressure P1 and P3, because they are not given, only the velocities are given as a boundary condition. So calculate what will be the boundary pressures. And there is the initial guess, that is UB star, UC star equal to 15. And you are given the pressure guess, that is PB star, PC star, P1, P3 star can be taken as 120. So that is given in the problem statement. The initial guess is given. Let us look at now the solution using the simple algorithm. Then essentially we'll start. Same point will be, we have to integrate the momentum equation on cell B and C. That means discretize the momentum equation on cell B. That is first step. Cell B has phases 1 and 2, if you look at here in the diagram. Right. Uh, that is the first step. We need to integrate from 1 to 2. And let me write the integration. Solution. Discretize momentum equation on cell B. So from 1 to 2, C mod U dx plus 1 to 2 dp by dx to dx equal to 0. Okay. And after integration, you will get the equation as C of B mod U B del X U B plus P2 minus P1 equal to 0. So your equation is somewhat like AB UB is equal to P1 minus P2. This is your AB. Sure. And you need to underlax the equation 1. AB by alpha and PUB is equal to P1 minus P2. This underlaxation equation we have already written in our previous tutorials. Plus 1 minus alpha U. Sorry, alpha U. Yeah. Here also alpha U. Alpha U into AB UB. Yeah. So this is your AB term, and this is your whole term is BB term. Okay, so your equation will look like something to be like this. So AB UB is equal to P1 minus P2 plus PB. Discretize equation under relaxation for cell B. Right. Let us say this is your equation 1 without under relaxation. And this is your equation. Okay. Any doubts? Similarly, you can discretize the momentum equation for cell C as well. So let us see. Momentum equation. The equation will now be from integrated from 2 to 3 for cell C. C mod U dx plus 2 to 3 EP by dx into dx equal to 0. So equation will be CC QC del x QC plus P3 minus P2 equal to 0. This can be written as AC. So the equation will be ACUC is equal to P2 minus P3. We can write this equation as number 3. And you underlax this equation. The underlax equation will be AC upon alpha underlaxation function. QC is equal to P2 minus P3 alpha U ACUC that. Okay. So equation will be given like ACUC is equal to P2 minus P3 plus PC. This is your equation number 4. So this is underlax for cell C. You have this equation 2 and 4 for cell B and cell C 2 and 4. Now one more thing that we have to do different from what we have done in the staggered mesh is basically the boundary condition U1 and U3 are given, but we do not know the pressures for these equations, for these locations are unknown. But in order to know them, we need relevant equations. So these are basically the same governing equation. It is just how the same governing equations control how pressure and velocity are related. Hold on, just a second. So these are the two equations we have, but we don't know the pressure for these locations, right? These are unknown for us. It is just the governing equation controlling the pressure and velocity. We need to find the pressure instead of making the approximation. What do? We take an approach where discretize governing equation on this kind of a half cell. So right here, boundary conditions U1 and U3 are given to know P1 and P3 values. No P1 and P3 values. We need relevant equations. To consider the discretization of half cell, centered around 1, around the 1 piece. So what do you mean from here? So we are taking this half cell. Okay. That is del x by 2. So take a half cell with the centroid assumed to be at 1. We have a half cell that is kind of like this. So you can see we are not taking the centroid to get this at the cell center. Essentially, taken the cell is like this, and it happens to be its represented value in order to derive an equation about pressure and velocities on the boundaries, which would be needed to update the pressure. So if I consider a control volume from 1 to B, okay, so C mod U integral is equal to 0. Okay, so let me do the integration, that is 1 to B one to B dp over dx equal to 0, and C1 Q1 del x by 2 U1 plus PB minus P1 equal to 0. So this can be written as A1 U1 is equal to P1 minus PP. This is our equation number 5. And if you under relax this, you will get A1 by alpha U U1 equal to P1 minus PB plus 1 minus alpha U by alpha U A1 U1 star. Okay, the equation will be A1 U1 is equal to P1 minus PB plus B1. So this is your equation number 6. Okay. We have got an equation that is basically a discrete momentum equation written for the boundary half cell for centroid one. And this is equation 5. We have done the under relaxation. This is equation 6. Okay. So you can similarly discretize half cell centered at 3 as well. So what we have done, equation 6 is basically the under relaxed discretized equation momentum for some kind of a half boundary cell, which we want to have because in order to apply the boundary condition and in order to get the value of pressure P1 on the boundary, we would need this equation. Because the previous equations didn't have the boundary pressures. Okay? But in the question, you see the boundary pressure P1 and P3 are required to be calculated. Anyways. Now similarly discretize half cell centered at 3. So again, you have a here like this. This is your cell C. You have 3. You consider a half cell center. Again, del x by 2. So again, you integrate from C to 3. C mod u x plus C to 3. dp by dx is equal to 0. P3 Q3 del x by 2 U3 plus P3 minus P3 equal to 0. So equation will come out to be A3 U3 equal to P3 minus PC. Sorry, PC minus P3. This is equation number 7. Under relax it. So what will you get after under relaxation? So A3 over alpha U, U3 is equal to PC minus P3 plus 1 minus alpha U upon alpha U A3 U3 star. So equation will be A3 U3 is equal to PC minus P3 plus P3. So equation number 8. Okay. So this is your discrete momentum equation written for half cell, basically centered or about phase 3. So now equation 8, 6 and 8 we have derived before these two equations. Relate the boundary pressure to cell pressures. Okay? Boundary pressure to cell pressure with boundary velocities. That means we got a relationship between the boundary pressure, cell pressure, essential in relation to the boundary velocity. And these are required in order to update the phase pressures from the velocities, phase velocities that are given, and the cell pressure that we would calculate. So that is the significance of writing this kind of a half cell thing, which was of course not there in staggered mesh case, because you already had the pressures and velocities are anyway staggered, and you never had to have such thing before. All right. So let us move on with the algorithm. Essentially, once you have written the discrete momentum equation, you can solve for them and calculate the heart velocities. Calculate heart velocity. Take a minute and think how and it will you proceed. Okay, then let us calculate the heart velocities. So we go back and list out all the 4 equations that we have for the cells. And this is essentially for the momentum equation for cell B and cell C, for node 1 and for node 3. So what we had was, let me write, ABUB equal to P1 minus P3 plus BB, and UB can be written as UB hat as EB, P1 minus P3. So UB hat is EB by AB, and EB is 1 over AB. This was for cell B, and for cell C, the equation will be ACUC P2 minus P3 plus PC. Okay. So similarly, we had node 1 and 3 as right. For node 1, equation was A1 U1 equal to P1 minus PB plus P1, and A3 U3 is equal to PC minus P3 plus B3. Similarly, you can write UC is equal to UC hat plus DC into P2 minus P3. We have just done all this above. UC hat is BC over AC. DC is 1 over AC. Okay. We have basically just divided the central coefficient on both the sides. That is how we got the velocities. Okay. So we would like to write these two in terms of hard velocities. So U1 is U1 hat plus D1, P1 minus PB. And U1 hat is B1 over A1. E1 is 1 over A1. Similarly, U3 is U3 hat plus D3 PC minus P3, and U3 hat is D3 upon A3, and D3 is 1 upon A3. Now, what is the main step? Main step in the algorithm on collocated grid is basically use momentum interpolation and calculate the phase velocities. So we have two cells, B and C. The only phase that we have is 2. The other two phases are the boundaries, 1 and 3, 1. And these are not very much interesting because the velocities are already given for them, U1 and U3. So we do not have to use a momentum interpolation to obtain the velocity there. And we will use the momentum interpolation and phase velocity to obtain the phase velocity U2. So what do we do using the momentum interpolation? We can write the phase velocity. That is U2 is nothing but your to obtain. You need to obtain the phase velocity. So U2 is the U sub U hat 2 plus the D2 times the adjacent pressures. So for a phase 2, the adjacent pressures are B and C. That means U2 will be equal to U2 hat plus D2 times PB minus PC. So we will call that equation 9. Let me write here. So use momentum interpolation. And obtain phase velocity U2. So U2 is U2 hat plus D2 PB minus PC. We'll write this equation as 9. Where U2 hat is nothing but UB hat plus UC hat by 2, and D2 is PB plus PC by 2. So this is basically a simple algorithm on collocated grid. This is the main assumption that we have made. So obtain the phase velocities through momentum interpolation given to the hat velocity and additional pressure. This is clear. So now once you have the momentum interpolated phase velocity, we can go and discretize the continuity equation. So in the context of staggered ratio meshes, we were discretizing the continuity equation or the pressure cells. Now in the context of collocated, you will discretize both the momentum equation and continuity equation only always on the single cell, that is the primary cell, which are basically cell B and cell C. Sorry. So you do not have any other cell to discretize. So discretize the continuity equation on cell B. So let me write. Discretize. The continuity equation for cell B. So from 1 to 2, we're doing UA equal to 0. Where U2 A2 from here will come out to be, we are writing next line. U2 A2 minus U1 A1 is equal to 0. Where U1 is known because it's a boundary condition. Known boundary condition. Okay. Then you can write in terms of prime and star values. U2 prime A2 plus U2 star A2 minus U1 A1 equal to 0. So from here, your prime value will come out to be U1 A1 minus U2 star A2. That is your equation number 10. So this is basically given boundary condition. You can split your U1 and U prime and U star. Okay. So U1 is a given boundary condition. This is the equation number 10. So what can we do? We can take the momentum interpolated face value in order to substitute the U2 prime. We have to go back and look at the equation 9. So that is your momentum interpolated face value and obtain the prime equation in terms of pressure corrections. So from equation 9, that is U2 hat plus T2 PB minus PC. U2 prime can be written as, I miss one A2 here. U2 hat prime is T2 PB prime minus PC prime. And from simple, we take this as 0. Right? Any doubts in this? So you discretize the quantity equation in terms of the in terms of the collocated mesh, both momentum and continuity equation, and the primary cell, which are basically B and C. Okay. Any doubts still here from equation 9? So this is basically from momentum interpolated face value. We have U2 equal to U2 prime plus the U2 PB minus PC. And if we subtract from the star corresponding values, you will have the U2 hat. So this is basically give you basically a U2 prime equals to U2 prime, that is T2 times PV prime minus PC. And again, using U2 prime would contain all the neighboring coefficients and everything which will be neglected as a part of the symbol algorithm. So U2 prime hat is 0. So that is what we are going to substitute for U2 prime in equation number 10. All right. On the right hand side, we have U1 A1 minus U2 star A2. So essentially, we obtain the pressure correction equation for cell B. Substitute U2 prime in equation 10. We get A2 D2 PB prime minus PC prime U1 A1 minus U2 prime A2. So this is your equation number level. Yeah. So this is a pressure correction in terms of PB prime, PC primes equals U1 A1 minus U2 star A2. So we have two pressure corrections that are unknown. We have obtained one equation. How do we get to the another equation? So we write the continuity equation for cell C because we have now written for the cell B. Similarly, if you write for discretize the continuity equation for cell C, that will be U3 A3 minus U2 A2 equal to 0. Again, U3 is given. Boundary condition, no. Okay. And again, you can write the U2 term part in terms of star and primes. So U3 A3 minus U2 star A2 star, or U2 star A2 minus U2 prime A2 is equal to 0. So from here, U2 prime A2 is U3 A3 minus U2 star A2. So that will also be equal to U1 A1 from mass conservation. This part. Okay, so you can write U2 A2 as U1 A1 minus U2 star A2. So from mass conservation, there's nothing. So I can write this equation in terms of this. So this is exactly the continuity. This is exactly the equation same we have got for cell B. If you see, let me write in terms of again the prime values in terms of this. So A2, D2, PB prime minus PC prime, U1 A1 minus U2 star A2. So your equation number. So if you see the equation number 12 and 11, both are same. The equation 12 and 11 both are same. So what we got here for cell B. Okay, so why the both two equations are same? So that means we do not have any additional equation. The two cells together is not giving you only one equation. This is because both boundary conditions are given for velocity. As a result, there is no boundary condition for the pressure. And therefore, the pressure that you have to obtain from this calculation, P, as well as if you have any constant to the pressure. So the both P and P plus constant will be solutions for the equation. As a result, you cannot fix pressure level. Rather, you can only find it up to a constant, right? Okay. Let me write this. Since equation 12, 11 are same, why? Question arises as both boundary conditions are given for velocity. No boundary condition for pressure. Therefore, you can say that P plus C and P both are solutions, right? As a result, you cannot fix pressure level. You can only find up to a constant. So you have to we can only find the pressure up to a constant because no boundary condition for pressure is given. But that is not a problem. That is not going to make any issue because we know that in compressible flows, it's only the pressure gradient that matters. It is not the absolute pressure that tries to give rise to the flow. So as a result, we would like to fix one of the pressure. So either you can take B prime equal to 0 or any other value or whatever you can take, and PC prime equal to some constant. Let us say PC prime is 0. So basically, there is some kind of a reference value for pressure corrections for cell C. So we are taking everything will come up in terms of PC prime. So if you once get the solution, you can change PC prime to something else. Everything will get added up to that. That means PC prime is 0. What you have added to A2, D2, PB, which will be equal to U1, A1 minus U2 star A2. Let me write here. Fix PC prime equal to 0. Reference value for pressure correction. For cell C. Then you can say that D2, A2, PB prime is equal to U1, A1 minus U2 star A2 from this equation. Equation number 12 or 11, whatever, both are same. Okay. So from here, PB prime will be U1, A1 minus U2 star A2 by D2, A2. Where U2 prime is D2 into PB prime minus PC prime, and U1 equal to 0, U3 prime is equal to, because these are known values. Whereas U2 can be written as U2 star plus U2 prime, and U1 prime is nothing but PB prime. P3 prime is nothing but PC prime. And P2 prime can be written as PB prime plus PC prime by 2. Okay. So pressure correction for cell B, once you know the velocity correction, you can calculate. But we also know the U2 prime. Once you know the PV prime, you can update with the velocity correction at phase 2. Okay, that is this U2 prime. And once you know the U2 prime, you can add it to U2 star and update your value on the phase. And also, we know that our boundary conditions are given for phase 1 and 3. U1 is given, U3 is given some value. No correction for U1 and U3 is required. That is why they are equal to 0, the prime values. If we go to the equation 6 and 8, U1s are related in the way you tell me. So if we go to equation 6 and 8, U1s are related. So essentially, we are talking about U1 A1 equals P1 minus PV plus P1. So U1 prime equal U1 prime. You would neglect that one. From equation 6 and 8, I'm saying. Okay. This was your equation 6, right? So equation number 8 is this for 3, and 6 is this for U1 and U3. Under last equations. Any doubts? If you check the equation 6 and 8. So let me write here directly from equation 6 and 8. You can say that PB will come out to be PB star plus alpha P PB prime, and PC is equal to PC star plus alpha P PC prime. And UB prime, cell corrections used for improving the conversions. The UB prime will be PB into P1 minus P2, and UC prime is PC into P2 prime minus P3 prime. UB is UB star plus UB. UC is equal to UC star plus UC. So we have all the pressure corrections. In doubts? The pressure correction on the phase one is same as the pressure correction on all the cell membranes, cell centroid. So the pressure could be different. You have to remember that the pressure correction is the same, not the pressures. The pressure could be different. P3 prime equal to PC prime. This is coming out from the applying the momentum equations to the boundary cells. And using the discretization, we are able to comment on the pressure corrections on the phases. And if you have a central difference approximation, you update the pressure on the phases, phase 2 as PV equal to PV prime plus PV by 2. Okay. So we have all the pressure corrections available. And we have to do is we have some kind of the corrected pressures. So cell pressures are PB equal to P star plus alpha times PV. We have some kind of under relaxation here. Similarly for PC, then you correct the velocities at the cell centroid. That is UB prime is equal to DB into P1 minus P2 prime. So these are again coming from the corresponding cell equations. We are doing this only to increase the convergence or improve the convergence. Then you correct the velocity correction to the start values. So again, these ones. So to improve the convergence. And one more thing is still remaining is basically you need to update the boundary pressure. We have calculated what is the pressure correction on the faces, but we need to update the pressure on the boundaries. So how do you update the pressure on the boundaries? Again, from the momentum equation, if you remember, we had U1 equal to U1 hat plus T1 to T1 minus. Okay, so let me write it. So that was the equation D1 times P1 minus PB. So that equation, if we recast, it's an equation for pressure on the boundary. That is P1 equal to PB plus U1 minus U1 hat. Okay, and even something kind of that. So everything is known on the right hand side, and the boundary pressure can be updated. So let me write the correct or update phase pressures. So your P1 is equal to PB plus U1 minus U1 hat by D1, and P3 is equal to PC minus Q3 minus Q3 hat by D3. So your P2 will be PB plus PC by 2. Updated pressure on the interior face from neighboring cell values. Okay. So essentially, we update the pressures on the interior faces from the neighboring cell values using the arithmetic average, and that completely finishes the algorithm. And we can go back with the new pressures and new velocities and then continue doing this. This is about the simple algorithm on a collocated fluid. And the code has been discussed by the professor in the lecture videos. If you go and see, the code has been discussed by him. Also, he has discussed some things about if I remember, on the unstructured collocated algorithm for unstructured meshes. So this is all from my side. So we discussed today all these things, starting from the Rieschauer momentum interpolation, then how we apply the simple algorithm on the collocated grid. Use the momentum. These are the momentum equation. Discretize them at cell center at P. Then momentum interpolation to obtain phase velocities. Then we get from the momentum interpolated velocity, we'll get the velocity corrections. We substituted them back. Then we did a question on that. And this question was quite lengthy, I know that. Okay. So in this question, you had first discretize on cell B, then you under-relax it. Similarly for cell C and under-relax it. Okay. So then you consider the discretization of half cell centroid around 1. Then you again under-relax it. Same thing you do for cell centered at 3 as well. Then you under-relax, calculate the heart velocities. Okay. Then you use momentum interpolation and obtain the phase velocity. Then you discretize this continuity equation for cell B as well as for cell C. Okay. Then from here, you get the updated pressures, correct or updated phase pressure values. All right. This was all, and you go back to the previous step and similarly solve the equations. Okay. So this was all, and this was my last tutorial lecture for you all. And I hope you all will be watching the videos, revising once again, revisiting everything. And all the content is available on the YouTube. The sheet has been uploaded. All the notes are available in the description there as well. The lecture videos are also from the prof are also available on the SWAYAM portal. So that was all from my side. The course ends here. So 13 weeks of tutorials and 12 weeks of the lecture videos. To finally finish up this course CFD using FVM. Right. So if you have any doubts, you can reach out to me in the comment section of my channel. I'll ping you there. Okay, or to the Google form discussion in the SWAYAM portal. And you can also check out anything on the LinkedIn. Also, you can post me anything. You can message me if you want. You can search my name and you can get back to me. All right. So let me end the session, stop the recording.